So that periodic table is the one that you will get to use on any quizzes and tests that have to do with naming and formulas, which is our next unit, okay? And if a metal is in the red zone, you will use a Roman numeral. And if it is not in the red zone, and if you want to, you can color it, like if you have one of those like lovely light colors or whatever, or if you would like to borrow one of my pencil crayons, you could, in theory, color it some other color. I just did not get around to doing that because it's a little bit of a pain. But all of these ones all of these metals and all of these metals do not use a Roman numeral. Yes? And everything else is either a metalloid or a non-metal, and they don't use Roman numerals either. So it's only the red zone metals that use a Roman numeral. So that's what this periodic table is for. So try not to lose this one. If you lose the one with the red, you'll get one with gray, which is just a little bit less exciting. Okay? It just costs a little bit more to print with color on it. All right, so that's one of the things you have. Another thing that you're going to get is a table with polyatomic ions. And it is pink, P for pink, P for polyatomic ions. And actually, do you want these today? We probably won't be using them today, or do you want to just like hang on for a little bit? You want it today? No. If you would like one today, come and get one. There, how's that? And I'll just hand them out to everyone else another day. Yep, it's stapled, so. Now, Unit 4. So, to be honest with you, Unit 4, you've done it in grade 9, you've done it in grade 10. There's very little that we learned this year that you haven't done 2 years in a row. We do hydrates and we do acids this year, in addition to what you've done before. So chromatography will be included in Unit 4. So when you're finished writing up the lab, I would take that chromatography review sheet, the chromatography lab technique sheet, and you can put it in your duotang or your binder along with the rest of Unit 4. So file this with Unit 4. You don't have to do that right now, but you will want it to be with Unit 4. And if you've lost it, just let me know. I will find you another copy. Okay. Chromatography, what the heck is it for? Well, first of all, do you guys know what the prefix chrome stands for? Chrome means colors. And what are you separating when you are doing chromatography? You are separating different colored substances. So, chromatography is a technique for separating mixtures. It's a technique for separating colored substances. Oh yeah, absolutely.
Sorry, I lost it.
No, it's okay. There you go. Right there. Anyone else need a chromatography sheet? Or you will need one? Oh, you are not here. You are welcome. All right. So what the heck is the strategy here? What we do is we flow a mixture over a material. And in this case, our mixture was food coloring. Yes? Food coloring over a material. And our material was the chromatography paper. Okay, so I'm just going to call it paper. All right? And then there's this language here. It says it retains some components. I really should rewrite this because retains some components. Anyone know what that means? That's what I thought. Okay, what it means is that some of the colored substances stick to the paper more than others. Okay? Some of the colors stick to the paper more than others. So what happens is the different components, in other words, the different colors, flow over the paper at different speeds. So here's a little an analogy for chromatography. And there used to be a little animation that went along with this, and it makes me so sad that it's gone. If any of you would like to make an animation, as like, if your grade is not as happy as you would like, and you'd like to make an animation that shows something like this, and make a little YouTube video for me, I would not say no. You know, talk to me about it, right? So we have this mixture of bees and wasps. I know they don't look like bees and wasps, they just look like little blobs, but let's pretend they look like bees and wasps. And they are swept by the wind over the flower bed, okay? So basically what we have here is we have the bees. Let's say the bees are represented by the color blue, B for blue, B for bees. Here we go, blue, 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 blue. There must be another one. Blue. Okay? So they represent the blue food dye. Although in our case, the blue went further. So never mind. It's okay. This is a different blue. All right. And we also have the wasps. And the wasps are going to be yellow. Here we go. Wasp, 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 wasp. And the wind is blowing. Yes? I'm such an artist. Okay? The wind is blowing. Which direction are the wasps and the bees going to move? They are going to move to the Right. Yes? Now, the wind is the water. And the flower bed is the paper. So here goes the wind. All the wasps and the bees are being swept to the right. But the bees are better pollinators than wasps. So what do the bees do? They stop at the flowers. Where'd it go? Blue for bees. Bee, 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 bee. So the bees visit the flowers. In other words, what do the bees represent? The blue dye. The blue dye sticks to the... What are the flowers? Paper. So in other words, the blue dye, which is the bees, sticks to the paper. Is this making sense? Okay, cool. Now the wasps, they don't care about the flowers as much, so they just travel with the wind. So the wasps, which is the yellow dye, stay airborne in the wind, and the wind is the water. Now, eventually the wind is going to blow the wasps all the way to the end, yes? But the bees will not have gone as far because the bees stick to the flowers. So what you can see is that you'll end up with the wasps further along, the same distance as the wasps travel the same distance as the wind, and the bees travel less far. Yes?
So that means if a food dye or whatever, or in this case, the bee, the
Yeah.
dial's less distance, does that mean it's more attracted to the paper?
That means it's more attracted to the paper.
Okay.
Yes. So in your lab, if a dye travels less far, that means it spends more time stuck to the paper. So it is more attracted to the paper. Does that make sense? So actually, I need a volunteer because we're going to demonstrate this. Yes, thank you. Okay, come on over here with me. This is the paper. The desks are the paper. You with me? Desks are the paper. So what's going to happen is that the water, actually I need one more volunteer. Yes, excellent. So sky is going to represent the water. Okay, the front of the water. There's water all behind, but you're going to be the water and you're going to travel. Now you are going to be the blue dye, which in our case, did the blue dye go far or did the blue dye go not far? When you did it. When you did it. It went further. So you are going to travel with sky. Okay? And I'm going to be yellow dye. Oh no, I'm going to be red dye. And the red dye did not travel as far. And I'm going to get stuck to the desk as we go. So we're all going to start at the same place. Okay? So we're all starting at the same place. This is that line. You remember the line on your chromatography paper where you started? That's your start line. All right, start going. Stuck. Dissolve. Stuck. Okay, you see how they made it the same distance? But I'm stuck, and then I dissolve, the water's still moving, oh, I'm stuck, right? And then I dissolve. So the more sticky the substance is to the paper, the less far it will travel. Thank you guys so much. Did that make sense? Okay. All right, so a dye that moves far spends more time in the water and less time stuck to the paper. Now, do you guys remember the word soluble?
Yes.
What does soluble mean?
Easier to dissolve.
Soluble is more easy to dissolve. So a dye that moves far and spends more time in the water and less time, that should say stuck to the paper, not stick to the paper. I'm so sorry, that's like stuck to the paper. Is that a more soluble dye or a less soluble dye?
More soluble.
That is a more soluble dye. Now, if we have a dye that moves not as far, that moves only a smaller amount, does it spend more or less time in the water? It spends less time in the water. And more time stuck to the paper. Does that make that dye more soluble or less soluble?
Less.
That dye would be less soluble. Okay. Now, let's take a look at, shall we take a look at this video? I'm not sure we should. Yeah, let's do it. What the heck? It's only 6 minutes, okay? It's not going to take us long. All right. GCSE Chemistry, paper chromatography number 63. Okay. GCSE Chemistry, paper chromatography number 63. There it is. Okay. Okay, is my sound all the way up? Not yet. Okay.
Communicate in English easily.
primarily explore project.
In today's video, we're going to talk about paper chromatography. We'll take a look at how it's done, explain the theory behind it, like what the mobile and stationary phases mean, and also show you how to calculate RF values. Now, chromatography is a general analytical technique used to separate the different substances in a mixture so that we can then identify them. And there are actually lots of different types of chromatography. But the one you need to know about is paper chromatography, which can be used to separate the different dyes in an ink. The first step is to take a piece of filter paper and use a pencil to draw a line near the bottom of the sheet, which we call our baseline. Next, you want to add your sample of ink, which you think might contain lots of different substances, to the pencil line. Then we need to find a beaker and fill it with a shallow amount of solvent, like water or ethanol. We are now ready to start, and we can place the filter paper into the solvent. But importantly, we have to make sure that we don't submerge our pencil line and our spot of ink, which is why we made our solvent shallow. And if you're being careful, you should really place a lid on top to stop the solvent from evaporating.
Now, we didn't worry about putting a lid on top to stop the solvent from evaporating because water doesn't evaporate that quickly. But if we had used alcohol, ethanol evaporates much more quickly. Have you ever had, like, what's a good example? Even, this is not an awesome example, but like hand sanitizer is partially ethanol. And you know how it feels cold when it goes on? That's because that ethanol part is evaporating. The reason it doesn't evaporate super quickly is because there's also a gel in there. And it's only like 75% ethanol. Okay? Now, don't submerge. Stop the solvent from evaporating. I actually did a run with some ethanol, and it gave me some better separation of some of the dyes. So if you ever want to, you can play around with different solvents because the different dyes will have different solubilities in the different solvents. You'll get a different result if you use a different solvent. Okay.
Then we just wait for the solvent to seep up the paper, and as it does so, the different dyes that make up our ink will dissolve in the solvent and move up with it. What makes this interesting though, is that each of the different dyes will travel up the paper at different rates, and so they'll end up separating out, which tells us that each one must be a different substance. So we've basically separated out the different substances. However, if any of our chemicals aren't soluble in that solvent, then they won't be able to dissolve and move up the paper, so they'll just stay on the baseline. Once the solvent has almost reached the top of the paper, we take it out and leave it to dry, and the pattern of spots that we have left is called a chromatogram.
And what should you do the moment you take it out? Start measuring, drawing your lines and circling things, yes?
Now, to explain why the different chemicals move up the filter paper at different rates, you need to use a couple of weird terms: the mobile phase and the stationary phase. What makes these things odd is you don't want to think of these phases as periods of time.
Now, what I'd like you to think about is I would like you to think which one is the mobile phase and which one is the stationary phase in our paper chromatography. And your choices are water and paper. Which one is the mobile phase and which one is the stationary phase? Yes. The mobile is the water and the stationary is the paper. Okay.
But rather as types of substances. The mobile phase is a substance that the molecules can move in. It's always a liquid or a gas. And in our paper chromatography, it would be the solvent that we used. Meanwhile, the stationary phase is a substance or material that the molecules can't move in. So usually a solid, or sometimes a really thick liquid. But for us here, it would be our paper. During the chromatography experiment, the different chemicals in our sample of ink will constantly change between the mobile and stationary phases, dissolving in the solvent, moving a little bit, and then binding to the paper, over and over again. And so overall, how much time they spend in each of these two phases is going to determine how fast they move up the paper.
Okay, so which of these three spots is the most soluble? Tell your partner, which of the three spots is the most soluble? What color? Blue is the most soluble. And who is the least soluble? Orange.
With the chemicals that are more soluble in the solvent, spending more time in the mobile phase, and therefore moving faster, and those that are less soluble, or are more attracted to the paper, spending more time in the stationary phase, and so moving more slowly. So if you think about it, how far each of the chemicals travels is dependent on the properties of that substance.
What distance have they measured there? What did we call that distance? D1. So those are all D1s. D1 orange, D1 pink, D1 blue.
And if we did the same experiment again, our chromatogram would look the same. This means that if we measure how far each substance moves, we can compare those values to a data book and identify which type of chemical it must have been. How far each of the chemicals moves, though, is also going to depend on how long we leave the experiment. So instead of comparing the actual distance, we instead calculate a ratio called the RF value, which is
Now, tell your partner, what's the RF value? Which number do you put on top and which number do you put on the bottom?
So, about the primary color, like how first in these pictures, like more purple and primary color, and they travel less.
So which number goes on the top? One number goes on the top, one number goes on the bottom. Which one goes on the top? D1. And D1 is the distance traveled by the solvent or the solute? What are the dyes? Are the dyes the solvent or the solute? They are the solute. So D1 is the distance traveled by the solute. D2 is the distance traveled by the solvent. Yes.
equal to the distance traveled by the substance divided by the distance traveled by the solvent. So if this pink substance had traveled 6 centimeters from the baseline, and the solvent had traveled 10 centimeters, then our RF value would be 6 divided by 10, so 0.6.
What's missing from that calculation? Units! What should be on the top and what should be on the bottom? Centimeters and centimeters. And what should the unit of RF be? Nothing, because centimeters cancel with centimeters. Excellent. Thought I said play. Oh, I did press play. Okay.
One of the important things to appreciate with chromatography is that when we do chromatography with a pure substance, so a substance with only one type of chemical in it,
what do you think will happen if you have a pure substance? What will you see on that chromatogram? Tell your partner, what will you see if you have a pure substance? Let's take a look, find out.
then it won't separate out at all. We'll just get a single spot on our chromatogram,
So
for which
pure
we can calculate
substance,
a
single
specific
spot.
RF value. However, if we did the experiment again with the same substance but a different solvent or a different type of paper,
What do you think would happen if we had the same substance but a different solvent or a different type of paper? And we let it run for the same amount of time? First of all, would we have one spot or two spots? It's the same substance, still one spot. Would it travel the same distance?
Maybe not.
Maybe not. It just depends on what the solvent is and what the paper is. Yep.
then the chromatogram might look different. And our RF value would be different too, because we'd have changed the mobile or stationary phase. So when a chemist looks up an RF value in a databook, they'd have to take into account which solvent the experiment was done in and what type of paper was used. Anyway, that's all for today. So hope you enjoyed this video.
Was that video helpful?
Pretty good.
Yes? Okay, good. I'll keep it in then. All right, so this is just like pictures of what happened in the video should you ever want to review them. It takes up a lot of space. I'm sure I could make it smaller, but you know, there we are. All right. Carrying on. La la la. And actually, where it says RF value, we are going to add in, when it says the distance traveled by the substance, we're going to add in the word the solute, the dye. Okay. So feel free to flip through until you can find that page. I should really number them. And in the RF value, we're going to add in centimeters, we're going to add in our units, and we're going to show the fact that they cancel. And RF has no unit. Okay. Okay, so here is a chromatographic animation, chromatographic separation explained VT chemist. Okay, let's go see that one. Yes.
Yes.
There we go. Huh? Skip. Big.
All right, let's begin discussing a little bit about how chromatography works. I want to give you a quick rundown and an animation of some of the underlying.
Do you want to watch the animation? I mean, we've talked about the bees, we've watched the little thing. Do we want to watch it?
We're good.
Oh, I got one who wants to watch it. I got a couple. You can, you know what? You can just chill. If you don't want to watch it, you can just chill.
How does partitioning between stationary and mobile phases help us separate the components of a mixture? So we're going to get down to the underlying.
Yeah, you know what? This guy's too low. His voice is too low. We're going to skip it. If you want to watch it, it is available on your worksheet. All right. Now, what has happened here? It has frozen on me. That's great. I love technology. Okay, here we go. All right, if you want to read this, you can read this. I don't think it's really, really necessary. If you're wondering what RF stands for, there are two different meanings. It can either stand for the retention factor or the ratio of fronts. You're not responsible for knowing either of those. As long as you know RF, you are good to go. All right? Let's see if there's anything in here that is useful to you. This is a dye. Okay, so here are some blue, yellow, and red food dyes. So here's blue. Here's yellow. And here's red. So these are fairly complicated molecules, yes? And they all have little bits on them that will be more or less sticky to some paper. So here is a question for you. This practice number 1. So if you can flip to the page where it says separation of food dyes, you've got this little picture and it says practice number 1. So here on the one on the left, our solvent is water. On the one on the right, our solvent is isopropyl alcohol. Okay, and what they want to know is which dye, red or yellow, experiences the greatest intermolecular attractions with water. Now, if you experience lots of attraction to water, does that make you more or less soluble? If your attraction is to the water, you are attracted to the water, that makes you more soluble. So which dye, red or yellow, experiences more attraction to the water, is more soluble? Yellow. Thank you. And which dye experiences greater attractions to the isopropyl alcohol? Red. Okay. Practice number 2, use a ruler to measure D1 and D2 for the blue dye and water. I'm going to let you do that on your own. Okay. And the answer is here. You can use that as practice when you're studying for your test. Yes? Does that make sense? Okay. And that's it for that. So, questions from the lab. What have we got?
Oh, I got one.
Yes.
This one.
Tell me.
If I'm a primary color,
Primary color.
I can't be broken down because I'm a primary color.
That's right. You cannot be broken down because you're a primary color.
I'm just making sure there's no exception.
Yeah, no. Now, sometimes dyes will have, like, you'll have a blue dye, but it'll have a little bit of red in it to make it like a more blue, reddy blue. You know what I mean? But
Like a true blue can't be broken.
true blue cannot be broken down. No. All right. Other questions from the lab? Are there any questions from the follow-up questions? Analysis? Yeah.
I have to answer all this question. And
You have to answer all of the analysis and all of the follow-up questions
separate paper.
on a separate paper. Answer all the analysis, all the follow-up questions. Write a conclusion. And that's all going to be on your own paper. Yeah.
Can you have like a brief explanation of for number 1?
For number 1, yes. Follow-up number 1. Follow-up question number 1. You have a chromatogram. This is on the back page of your lab. And we have our line here, we have this here, we have this here. And we are told that the sample was, what color was the original sample? Everybody look at follow-up question number 1. Tell me what color is the original sample?
Orange.
Orange. So you are asked to identify the dyes in this sample. Now, first of all, what colors are you limited to? If you have an orange sample,
Yellow and red.
yellow and red. Yes, so I don't want you saying, I found that we have blue dye number 1, because does blue help make orange? No.
Where does it say?
Where does it say orange? It says it in the 3rd line of follow-up question number 1. Yellow and red. So what you're going to do, you are going to measure D1, and you're going to measure D2. And this is going to be spot A. You're going to calculate the RF of spot A, and you are going to compare it to table 4, okay, which is on the previous page. You'll just do this exact same thing for spot B. Does that make sense now? Cool.
Thank you.
No problem. Anyone else got any questions? I can turn the lights up again so you can see it better, sorry. Nobody wants to know about follow-up number 2? Yes.
Can I redo my atomic ions, please?
Not right this second, no.
For number 2, do you just do algebra?
For number 2, do you just do number 2 is just algebra.
Yeah, that's fine. Oh, I had a question, right?
Follow-up number 2 is algebra. Yes.
Oh, wait, for this one, did you say it was yellow and red?
Yeah.
This one's yellow and red.
Yeah.
But if you like, is this the starting point?
Yeah.
But if you travel like.
So yellow is more soluble in water than red. Red is more soluble in isopropyl alcohol than yellow.
Oh, okay.
Yeah.
I was like reading it says experiences greater attraction for water. I thought that's like.
Greater attraction for water means more time in the water means more soluble.
Oh, so that's like different from attracted to paper.
Yes, yes, exactly. Yeah.
I'm good.
We're good? All right. Do you need any time to work on the lab right now? Yes? Okay. Can work on the lab till the end of class. We will start Unit 4 tomorrow. Oh, the only thing I want to tell you about Unit 4 is you should memorize your prefixes. Mono. What comes after mono? Di. Tri. Tetra. 5 is penta. Hexa. 7 is hepta. 8 is octa. And 9 is nona. And 10 is deca. And you need to memorize these because quiz number 2, like basically this next unit, you're going to be doing quizzes as fast as you can. Okay? There's 11 quizzes to get through. So you want to do like multiple quizzes per day. Now, given that quiz number 1 is like, what's the compound between sodium and chlorine? And you'll be like, sodium chloride. You'll be able to do that one. Okay? And then quiz 2 is like, what's the name of NO2? Nitrogen dioxide. And then quiz number 3 combines the two and says, can you tell when to use prefixes and when not to use prefixes? Okay, so quiz number 1, 2, and 3, bam, 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 they're going to be really fast. So memorize those prefixes.
Oh, Miss Beth.
Yes.
I need to watch it and I also get the sheet what.
Yes. Yes. I'm sorry, it doesn't have your name on it anymore.
That's fine.
Okay. Quiz. Ion quiz. Ion quiz. Where did I find it? I found it over there, here, Ions. Oh, brain, can you please brain for me? Not there, not there. Lewis structures average atomic mass. Okay, so I got it somewhere else. There you go. That one? Okay, those are the prefixes that tell you how many there are of each atom in a covalent ion. So like if you have carbon dioxide, it tells you there's 2. Okay, yeah, and you'll have the weekend to memorize them. Okay? But I thought I'd give you a little extra warmth so you could start studying today. Yeah. Yes.
What is question one asking?
What is question 1 asking? Which of the colors tested by the class in the experiment appear to contain one or more of the proved dyes listed in table 4? So you have an RF of 0.866 for yellow. Yeah, you're correct. That one doesn't seem to be in there. But 0.97 is really close to 1. Isn't 0.97 really close to 1?
Mm-hmm.
So when you say no here, you're saying no, this is not close to 1. Does that make sense? Or should you change that to a yes?
Change to a yes.
You should change that to a yes.
So what was like these 2 points? Like, am I supposed to ask those?
Okay, so what it's telling you is if your RF value is within 0.05 of the standard, it's a likely match. A value further than 0.05, actually, I think it should say 0.5. No, 0.05, that's right. A value further than 0.05 is probably not the thing. I think I got like half a sentence here. Yeah, that second point doesn't make any sense because it's got 2 sentences combined. Yeah, sorry about that.
Okay.
Yeah.
Okay.
Okay? Yeah.
You're supposed to answer that. No, on the first one. That you
Oh, on the first one, Which of the colors tested by the class appeared to match? Well, you told me that, so you would say the blue in the green food coloring appeared to be blue number 1. The yellow in the green food coloring appeared to be yellow number 6.
Okay.
Does that make sense? And then you would do the same thing with the unknown.
And for this one,
Yeah.
none of them match, so I can just.
So you can just say none. Yeah. Yeah. Hi.
Do for the conclusion.
For the conclusion, you're going to write the heading conclusion, then you're going to state the results to objective 6, which is to identify the components of mixtures by means of their RF values. So what would you say in order to identify the components? Which mixtures did we look at?
Just like the individual compounds.
So, yeah, but what did we call the mixtures? One of the mixtures was green, and the other one was the unknown. Okay, so you will say the components of the green, and we'll just go back here to take a look. Yeah. Okay, let's just double check here. So green, we have blue, 0.65. That's a really weird result for the blue. But that's okay. All right. 0.58 for the yellow. 0.69 for the blue. 0.58 for the red. 0.58 is close to 0.62, n'est-ce pas?
Yeah.
Yeah. So, but you said no, it's not.
Okay.
Okay.
For this,
So you would want to change that because, going back here, you could say green dye appeared to contain none of the dyes, and you'll go with your results. Some people's match, some people's don't. You would say none of the dyes from table 4, but the unknown appeared to contain red dye number, whatever the heck it was, no, red dye number 4, and an unknown blue and an unknown yellow.
so I just explained the results.
Yeah, exactly.
No, please.
Five A, which of the individual dyes, red, yellow, or blue, have the strongest attraction to the chromatography paper? So we have blue, yellow, red. Which one traveled the furthest? Blue. Okay, and which one traveled the least far? Red. So which of those two
Stuck to the chromatography paper.
the most?
Red.
Yeah.
Oh, okay.
Yep, yep.
Thank you.
Oh, good try. Oh, just six big matter here. Just like, all right, I don't know. Put it down.
Weird with algebra, you know what I mean?
It's kind of weird because I'm like,
Yeah.
after that,
Yeah.
so it'd just be like 100%.
Yes.
Give me a sec.
Yes.
Are we gonna have a final? No, right?
No. So, ladies and gentlemen, just in case you're wondering what to do with your Unit 3, you have an option. Should you choose to keep it, you can go put it in a binder at home. We are not having a final in Chem 11. So, because quite frankly, is it Unit 7? Anyway, whatever our last unit is, covers almost everything anyway. So I'm not going to worry about it. Okay? Yeah. So up to you whether you keep it or recycle it. Yes.
Good.
I'm gonna say today it's too much for me. I just like yesterday. It was crazy, but I'll know. You don't know by tomorrow. Okay. Yeah. Yeah.
You don't know. Oh, well, let me check my shape. Nice. Sure. 2, 4, 6, 8, 14, 16. Oh, listen to something.
So lovely students, I'm going to just pop to the washroom really quick because I'm going to have grade 12s coming in here at lunchtime to start their tests. So I don't want to have to like not go to the bathroom during their tests. Whatever. Yeah. Oh yeah.
Có nhiều bài quá thì phải ba biết. Không, ba là việc
I don't really want to know.
nhưng mà ba không biết là gì vậy? Biết không? Ủa?
Yeah. Stabilize.
À, ta đừng nói là tại vì ta không làm mà ta biết khuya ta làm hết cái rồi ba mẹ tôi cảm thấy là con cái của con làm rất là chặt chẽ nhiều
Technically, the standard on yeah. Something. No. You should go watch it.
Con biết cái information.
I'm
Thì học sinh phải học thuộc. Nhiều bạn nó chơi.
Negative numbers. Okay. So you guys how much yes. So if we that's just weird. I did a bunch of unrated games before. I think unrated is awesome. I was like saying this like funny. Every game. That was like the main yeah, sure. And then I had the well, boys, let's take the card. I'll take the card. Take it over. Come on, hey, you're proud, don't let it go. It comes out. Yeah, I think it's fluent Chinese. Okay, but I'll be either down there. Yeah. Yeah.
It's not
Right. What am I gonna do?
Hey Christina, do you have a chem test right now? Oh.
Oh, you know, like, go to this. First, you know, like, one of the followers said, this year was, when we did, we were like, I think it was
traumatized by this now.
about do it.
I'm just about to go right on that.
Hey, welcome. First floor.
So if we find somewhere else to eat today, if you're good, you want to study, that's fine. Okay.
In a thousand years, all that. What's this?
So the lunch is canceled here today.
Okay.
You're studying for your 10-12 lesson.
This fast. Can you check out my shape? Right
Huh?
there.
No, I don't know what's happening.
I'm
There's
pretty
so
sure
many
it's
things
wrong.
happening right now. It's okay.
I took like a quick peek yesterday. No, like 2 days ago, I looked at the experimental page for like 2 seconds,
Uh-huh.
and I just
Okay,
guessed the shape.
okay, fine.
I think it's
Where
wrong.
are you? Oh my God, I can't even find your paper here. No,
Right? Or wrong?
you don't have enough electrons.
Oh yeah, I'm missing 2, right?
Yeah.
I'm
How can your structure not have enough electrons? That is not going to work. Okay?
Yeah.
Okay. Yeah. Yeah, I don't know where. No, so what you can do is you can either take that one and put it in a binder, or you can take this one and take it over in a binder, or.
Oh, yes, please.
Right?
No space and then every.
Okay, can I just tell you that I didn't discover these until like I was in like my 10th year of teaching. And I was like, ooh, this is like sort of the best thing ever. Anyway, so I invested in them now. Yeah, so they just, I'll be done in like 45 seconds. Is this? Yes. You don't need to do a second dissociation. You're never gonna need to do that, because it's like, does it make any difference? No, it doesn't. You never need it. Okay, yeah. Uh-huh. Okay, so you have 2 molar NaOH. Yes. So what NaOH does, a strong base. Yes. Mm-hmm. And that gives you the concentration of hydroxide, and then you can find. Yeah. done with that. Oh, there it is. Are you ready?
Mr. Gatsky, could you please call the office? Mr. Gatsky, please call the office. Thank you.
1.0 times one.
Oh.
Yes.
Oh, okay.
Yeah. And if you forget, it is. Yes. Okay. Yeah.
Yes. Wall was hard. Wall was really hard because outside you had to fully intestine stand. And we were on like 3 of us and they could have had. That was scary.
That's brutal.
Yes.
Yeah. I haven't seen them, but I'll ask them. Okay. Have you guys seen up this row? Have you seen these? I don't know. Let me check with the office. Yeah. Okay, I haven't seen it, but you're welcome to look around. Did you have them at the beginning of our block? Yeah, okay. Maybe, I would check the office, because if someone found them, they'll probably take it to the office. Okay. Sounds like something I would do. I think that's like old school. Yeah, I think so. I think it's from like my era. I feel. Right back teenagers like that for long. Oh, really? Well, you gotta imagine like before you get there. Right?
I just know there's a movie out for it. Oh, really? Yeah. So I heard.
Yeah.
So,
Yeah. It's been so long, I remember not. I read books, yeah, I read books every couple of years if I really like them, because I'm like, I just don't remember it half of them. Yeah, exactly. I get value bang for my buck. Yeah. Why is it so late? Why is it? It's. I'm like, you really take that to your why would you not take it? Okay. So salt is positive, negative, you'll have like either methyl or aluminum, and then another. Yeah. Yeah, so you have salt, that's an acid, nitrogen ion. Salt is neutral. Well, yeah, 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 yeah. And if you're honest, you're like, okay, hi. Uh-huh. That's because this is a OH. Is, then you're going to take 14 and subtract that to get. No, so if you calculate this is concentration OH, yes. So this is in pH. Oh. And how do you go from OH? This is so. Yeah. How do you have pH? Okay. If you're gonna do that, hydrogen, you need to use hydroxide as an oxidation, not pH. What you're doing is you're doing concentration of H concentration of OH, which is fine. You would just use this number. Yeah? And then you would take the negative log. Okay, or, fine, that's concentration of OH, that's your QOH. pH plus QOH is equal to 14. Yeah, so 14 minus that will give you pH.
Oh.
Yeah, yeah. Okay, I'm doing those. I'm putting them back. Good. Yes, from weakest to strongest. Yes. Okay, so that one. For that one, we have CaOH. That's all hydroxide, so it's strong. Yeah. How many hydroxide? Two volts. Now the concentration of CaOH. This will one. Okay, so you're now, so that's my concentration of OH. If I take the negative log, if I take the negative log of because it's the same time, that, that's the low. Now, you want pH. pH plus pH. H. So, minus. Yeah. It's not a compensation, but first of all, pH, and going to graph segments, you have more steps. And this one wants to OH, hydroxide, the less steps. And this one, we have hydroxides, so again, more steps. This is much more complicated process. This one, you only have one hydroxide, so it would be the same process. Yeah? Yes. Oh, I'll just be with you in a second. Yeah.
I'll transfer.
Uh-huh.
And then I don't know why.
Okay, because this one is a weak acid.
That's why.
Mm-hmm. Okay. Yeah. Okay, so. Yeah, so you will have, sorry, my pen doesn't work, so let's get this one, this pencil works. Okay, so we have calcium hydroxide. Dissociates to form Ca-2+ and 2 minus. Right, because that's you there. No. Strong bases. Yeah. There is, but only the first associating matters in the acids. Yeah. Whereas with the bases, it just comes all apart. Yeah, yeah. What am I doing? Right. I just want to. Okay. If it's on both sides, yes. Now, a hint for happy brother is that it's a negative sign, a negative, and a positive. Okay? So you notice NH3. Yeah. 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 Yeah.
So what's the
This is not a weak acid. What it means is we're really not interested in the hydroxide ion here, even though we list the hydroxide ion, we can list the nucleic acid. Okay? We're really interested in the one side because that's the one that we actually have to one. Yeah. Yeah, you know what? It really is. Yeah. Yes. Yes. Okay. So 1.8 times 2. That's because it is citric acid. 6 benzoic acid. So you use the wrong period. Well, They look similar. Here's ethanoic. Yes, that's the one you used. That's not the formula. You want benzoic. Ah. Yes. Yeah. Yes, of course. Okay. All right. Just grab a pencil there. And or something, pen will do. Here, we have NaOH, strong base, so NaOH. Strong base that these super. Yes, so add it. Now, so I want so this one table. Same question. Okay, because again, you've got sodium hydroxide and NaOH, so it's gonna come apart. The only thing that's gonna be different is the concentration, but that's still awesome. Okay, there we go, so it's the same. Okay. Yeah, all right, no problem. Uh-huh. Oh. You just take the negative, that's your hydrogen, right? So take the negative one. Yes. Yes. So if anyone would like to start early, or if you have questions, just let me know. Yes, okay, so, this is our first association, and this is our second. Yeah, so we have, let's just use a diprotic acid, let's say that one, for example. You want to see this as well? Okay. So we have H2SO4, for example, diprotic acid. And if you look at its first association, one two. If you look at the second association, now it comes to this guy. Okay. There it is. Second one comes out. And you notice this is a much weaker acid than that one. Okay? And you can prove that by saying this one's Ka value is much bigger than that one's Ka value. So which one gives off hydrogens more? right? Because products over reactants, so the larger this number, the more product you have. What's one of the products? Hydrogen. It's a lot more hydrogen. You can just say because it's got a smaller and probably, yeah. Yeah. Okay, yeah. Yes. Uh-huh. Yes. Oh, Jesus, too water. Yeah. Well, I mean, water is yeah. Whereas this one, it's not water. I mean, some people use it. I know what it means. I don't know, which then, yeah, I love some. Yeah. Oh, shoot. I'm supposed to call my son at 9. Hi. Sorry, I forgot you. Did you get up and going? Good. Just give me 1 second. You want to start?
Yeah.
Cool. There you go. So, how's your day? Oh, one of my students, they're writing tests at lunch. You want to start? Perfect. Right? Well, they get a little extra time because their class actually starts after lunch. So I told them because it's Chem 12. So I'm like, if you want a little extra time, you can start during lunch. Yeah. Okay. My son says good luck to you all. He's studying for finals. So everything else is good? Okay, good. I love you too. You have a good day. Okay, bye.